With the rapid advancement of automotive technologies, more and more vehicles on the road are now equipped with automotive radars. Radar exploits the difference between the transmitted and received continuous electromagnetic waves to obtain the range, velocity, and angle for a target. Radar is the key sensing technology to support intelligent pedestrian detection, blind spot detection, and intelligent park assist. Compared to LiDAR and camera, radar has the advantage of being able to work at night time and is not affected by bad weather such as fog and snow. As more vehicles are equipped with automotive radars, interference among the radars becomes a problem. Here we illustrate two scenarios for mutual interference. In the first scenario, the interfering radar is the target that needs to be detected. The signal transmitted by the interfering radar produces interference to the reflected signal. In the second scenario, the interference comes from another vehicle rather than the target vehicle. The interference radar may be closer to the victim radar than the target. In both scenarios, the power of the interference signal can be much larger than the intended reflected signal, which will severely degrade the performance of target detection and might result in collisions, injury, and even death. The de facto waveform in automotive radar is frequency-modulated continuous wave, or FMCW radar. There are two key parameters in the received FMCW signal: frequency slope and delay. Both are compared with the transmitted signal. Since each radar chooses its own slope independently, the waveforms of victim and interference signals are different in general. In the time-frequency domain, there is a low-pass filter at the receiver with a center frequency that equals the frequency of the reference signal. After the low-pass filter, the output interference signal will be time-limited. In the time-amplitude domain, within the interference duration, the signal power becomes much higher due to the addition of the interference signal. It also shows the time-limited property of the interference signal. As a result, the mutual interference between FMCW radars is time-limited and will reduce SNR. In the state-of-the-art, there are two categories of interference mitigation algorithms for automotive radar. The FMCW-compatible algorithms can be directly used on the current FMCW radar system on the road, while the FMCW-incompatible algorithms cannot and require a completely new design. We focus on the FMCW-compatible algorithms in this research. Among the state-of-the-art interference mitigation algorithms designed for FMCW, there are two classes. The first class is called detection suppression algorithms. In the detection step, one sensor constantly detects the interference in the environment and updates the detection threshold periodically. In the suppression step, a filter with a dynamic window system function is used to suppress the interference. Because of the single window system function, it can only detect and suppress one interferer, but cannot handle multiple ones. The second class is called compressed sensing algorithms. They use signal transform techniques such as Fourier transform, or short-time Fourier transform to explore the sparsity of the signal in specific domains to separate the interference signal and intended signal. Compressed sensing algorithms can handle multiple interferers. Although it has good performance, the complexity is very high and cannot meet the real-time requirement of the automotive system. Our objectives in this research are to design an algorithm that is compatible with the existing FMCW radar system, capable of mitigating multiple interferers, offer comparable or better performance than the state-of-the-art algorithms, meet the stringent real-time computation requirement in an automotive radar system. Our proposed solution is called Soteria, named after the Greek goddess of safety, salvation, and preservation from harm. Soteria is a real-time compressed sensing-based algorithm. It separates the intended signal and interference signal by utilizing the sparsity of the signal and leveraging a GPU's massively parallel computing. In the first step, both the intended signal and interference signal are transformed from the time domain to the time frequency domain, where the intended signal becomes a constant signal, and the interference signal becomes a sparse signal. To reduce computational time, Soteria performs short-time Fourier transform on GPU by running multiple discrete Fourier transforms in parallel. In the second step, we reduce the search space of possible interference signals by narrowing down the range of signal delay and slope. After this step, the search space is reduced from the original signal basis to a smaller but most promising subspace that exactly matches the number of available threads in a GPU. Specifically, the reduced range of slope is calculated based on the interference duration, and the reduced range of delay is obtained from the data of the previous time slot. In the third step, Soteria employs the orthogonal matching pursuit method, or OMP, that iteratively estimates the interference signals. In each iteration, all correlation factors of all possible interference signals are calculated in parallel on a GPU. Then we use parallel reduction to find the signal with the largest value as an interference. Once the interference signal is identified, it is eliminated from the signal space. Then Soteria enters the next iteration and goes through the same process to eliminate another interference signal. When Soteria completes all iterations, all interference signals are removed. Now we present the results of our experiments. Our hardware platform is an NVIDIA DGX station, which has an Intel Xeon CPU and a Tesla V100 GPU. For the software, we use the NVIDIA CUDA Toolkit 11.2 as the programming platform. The mobility model of vehicles is generated by Sumo. Here is the traffic scenario in our experiment. There is one victim vehicle, 5 targets with different distances from the victim vehicle, and either 1 or 2 interferers. We focus on the interference scenario where the interference comes from other nearby vehicles rather than the targets. When there is just one interferer, the blue curve shows the received signal when there is no interference. We see that there are 5 clear peaks, which represent the 5 targets respectively. The orange curve is the signal with the interference. The signal power becomes larger with the additional interference signal. We can only see one peak, which means the other 4 targets cannot be detected. This yellow curve shows the result from Soteria. Even with the interference, we can still see all 5 peaks, which means that all 5 targets can be detected. Further, we can see that the SNR is much higher after the interference is removed. This black curve below is the IMAT algorithm, which represents the state of the art. Only 4 targets can be detected. When there are 2 interferers, in the orange curve, no target can be detected because the interference is too high. In the yellow curve, which is Soteria, all 5 targets can be detected. In the black curve at the bottom, the state-of-the-art algorithm IMAT can only detect 1 target. We can see that Soteria's performance is better, especially in multi-interferer scenarios. Now we show the processing time performance. The time consumption of the data transfer between the CPU and GPU is included. In the 1 interferer scenario, the computational time of Soteria is around 5 milliseconds, which is much smaller than the state-of-the-art IMAT algorithm, which takes more than 100 milliseconds. In the 2 interferer scenario, the computational time of Soteria increases but is around 10 milliseconds, and the computational time of the IMAT algorithm is more than 100 milliseconds. We see that the computational time of Soteria is much smaller and can meet the real-time requirement. In this video demo, we presented our research on interference mitigation in automotive radar systems. We have developed Soteria, a compressed sensing-based algorithm that meets all our 4 design objectives. Soteria works directly on the existing FMCW radar system. It can mitigate multiple interferers and offer comparable or better performance than a state-of-the-art algorithm. It is the only known algorithm that can meet the stringent real-time requirement for an automotive radar system. Thanks for watching. Please feel free to contact us if you have any questions.